All right, let's get started. So we're going to continue from where we left off. We had talked about measures of centrality in our basic summary stats. And today we're going to talk about measures of spread. And as you're going to see, measures of spread are directly related to measures of centrality. We're going to cover a couple things here. We're going to cover the 5-number summary, IQR, variance and standard deviation, and we'll use IQR to kind of use an old school way to determine if something's an outlier. And if there's time at the end, we'll continue into the next topic. Sometimes there is from this lecture. This one might wrap up a little early. Okay, so let's consider first the 5-number summary. And we're going to continue off of that same document, summary_stats.py. We're going to put all of the summary stats in there. So 5-number summary, it's going to have 5 things in it, right? There are 5 things. So got the, oh wow. Sorry, I have a new drawing pad, and I'm not quite used to it. So 5-number summary. There are obviously 5 things that we're going to consider. We're going to consider the minimum. And if we're going to consider the min, we're going to consider the max. Okay. We're going to consider the median. Okay. So something to consider is that between the min and the median, there's a median, right? There's what we call the first quartile, or Q1. This is the median between the min and the median. And we're going to be inclusive of the median. I believe that's how we're going to do this. I have to double check my code to say for sure. There's actually different arguments for this. We could either include the median in the lower half or exclude it, but I learned it by exclusion, but I think most people will include it. So we'll teach it as inclusive. So again, the Q1 here is going to be this, the median of this, right? And Q3 is going to be the median of this. Yeah, so if you think about how to create the 5-number summary procedurally with Python, there are functions that we have that do a lot of this work for us. Okay, we've got the min. That's just the min function, right? Min. We've got the max. That's just the max function. That's easy enough. We have the median function from last time, and like I said, we're continuing from last time. I'll go ahead and paste in the mean and median functions just so that you have them. You will need them. So here we've got this already written. Okay, we've got a median function out there somewhere. And then if you think about this, you get Q1 by taking the median of all elements between the minimum and the median, right? And you get Q3 by taking the median of all elements between the median and the max. So with that in mind, let me give you those functions really quick. So you're going to need the mean at some point. So make sure you copy this in if you don't have it somewhere handy. And you're going to need the median. Obviously, you'll need the median for this one. So I'll throw that in there as well. All right. So you are going to code the 5-number summary. I'm going to give you 6 minutes on this. and maybe I'll give you a nicer thing to look at here. Give you that, and maybe I should give you some data. Yeah, why don't I give you a little bit of data to work with. So I'll just put this in the Slack. We'll do the list, a list that's composed of values between 0 and 200 by 5s. So this will be a very generic kind of list of data. And I'm going to make it a list explicitly, even though you could just you should just be able to pass in the range. Okay, so with that, let me give you just sort of a nicer background, and I'll set a 6-minute timer. So go ahead, code up the 5-number summary. You should be returning 5 things, and if you just do return, that minimum, comma Q1, comma median, comma Q3, right? It'll return all of that as a tuple. All right. So yeah, go for it. Okay, so let's go through a solution for this. This isn't the easiest thing to write. There's a lot of parts here. It's dependent on prior functions, but well, I think once you see it broken out, it'll be pretty easy. So we're going to say 5. I'll make this a little bit bigger. 5 number summary, right? And we're going to pass in, of course, we're going to pass in a list. So that's our starting point. What do we know we can get offhand? We know we can get the minimum. We can get the maximum. We can get the median. So I can call this min. Notice I'm doing min underscore. The reason I'm doing that is that min itself is a function. It's a reserved word, and I don't want to call this min like that, right? That's sort of an issue. So I'm doing min underscore. I'm going to get the max, which will just be max of list. And then since we have median above, right, we've got median somewhere here, right? Median's right there. I can just get the median, which I'll call med, and that'll just be the median of the list. So that's a good measure of the way there. Now, the next thing we need to do is determine the lower half of our data, right? How do we do that? Well, lower half would imply that we're in numerical order. So we're going to use the sorted function. I'm going to call sorted on list. And I'm just going to name this is our sorted list. Why not? And from there, we want to check a couple things. We want to check to see if that list is even or if it's odd in length, right? If it's even in length, then we're going to have, let me just do this. I'll show you. So if the length of the list mod 2 is 1, okay? Then we know that the original list is of odd length, which means that our median is going to be included in the lower half and in the upper half. Okay. So logically, I know that's maybe a little bit confusing. I think when we walk through this, it'll be a little less confusing. So I'm just going to say we've got a lower half, and this is going to be that sorted list, right? Where we're going to go from the 0th index up to the median, which for us is going to be the length of the list divided by 2. And like I said, we want to be inclusive here. So I'm going to say +1. All right. So that's our lower half. And I think at this point, it might make sense to just print this lower half to make sure what we have going on here makes sense. Okay, so I'm going to go ahead and call this function, make this a little bit smaller, and I need to generate a list, which I should just be able to use. Well, let's generate something actually much simpler. Let's do the range from 0 to 50, and we'll go by 5s. And I'm going to listify that. And here we'll also print the sorted list. So if I'm going to do this in kind of a step-by-step process, we'll be able to see this. Oh, whoops. That's an even number of items. So let's do 0 to 51. Oh. Option 5 float has no length. What am I doing wrong there? Ah, int. That's what's going on there. I'm casting to int here because we can't index with a float. Okay. So our lower half looks like this, right? We're including that 25, which is the median. And our upper half should start at 25 and include up to 50. Okay? So how do we do that? We can just do this. Let's say upper half. And this is going to be that sorted list. And in this case, we can start here and go to the end. So let's also print the upper half while we're at it and run this again. Okay, so notice our lower half goes from 0 to 25. That's good. Upper half goes from 25 to 50. So all we need now is the median of the lower half, median of the upper half. Although, you know, to be clear, we're going to need to also account for the an even length list, right? So that's going to be very similar, with one tiny difference. We're not going to do the +1, okay? And there are other ways that we could write this where we wouldn't have a conditional statement like this, and maybe I'll clean this up after. Yeah, I think we'll have time. I'll clean this up after so that you can see an alternative way of doing that. But let's just verify. I'm going to change this back to 50 so that we have an even length list, and we can see now we're including so the lower half 0 up to 20. The upper half 25 to 45. So that's the behavior we want. Once we have that, we can go ahead and just get the medians for Q1 from the lower half, the median for Q2, or sorry, for Q3 from the upper half. So Q1 is going to be the median of the lower half. If I can not make a typo there. And Q3 is going to be the median of the upper half. Okay. All right, so we have those now, and the only thing this function needs to do at this point is return everything. So what are we returning? We're returning the minimum, Q1, the median, Q3, the maximum. So here's our min, here's Q1, we've got our median, Q3, we have the maximum. So the assumption is that this is going to work. Let's find out if it does in fact work. I'm still printing the the entire list in order, but I think this makes sense, right? So in this lower half, if we're talking the even list, we have a median of 10. Or sorry, in the entire list, we have a median of 22.5, right? It's between 20 and 25. We have the median of the lower half as 10, the median of the upper half as 35, min is 0, max is 45. That's working as expected, and I wouldn't be surprised if we do the odd length list that's going to work as expected as well, right? So in this case, 25 is our median, 25 is included, and our Q1 is going to be the median that exists between 10 and 15, right? So 12.5. So I think we can see this is working in a way that we might expect it to work. So I'm going to grab all of this. I'm also going to comment out that print sorted list because you don't actually need that to do that. Put this in the Slack. And then I just want to show you. Great question. Couldn't I just use the median for slicing the list? I absolutely could. Yeah, absolutely. Yeah, and that's kind of what I'm going to get at. I'm going to refactor this just a little bit. So, you know, how do we want to refactor this? I could go ahead and we could start here. Let's start right here. So I could, instead of having a conditional, I could say, let's see. This is odd. I'll just call this odd, and I'll make this a statement, and then I can go ahead and eliminate this else and do something that you'll see me do in a few places. Instead of adding 1 here, I'm going to add odd. Okay? And if you get what that's doing, odd, if odd is 1, then, if odd is true, then that's going to act as a 1 arithmetically. So I just got rid of a bunch there. That's kind of nice. We could just call this the median of our list, right? We could just change this to median of list. What might be a little nicer is if we just take med, right? That should work. So med. Oh wait, what did I do? Oh, I see what I did. I did not get rid of all of that. So we could just take med there, median there. What else could we do to make this a little bit tighter in terms of the code? Well, we could, instead of making a min variable, we could just go down here and say min of list. We could do the same thing for max. We could say max of list. And to be clear, the reason I'm demonstrating this is not to say that this is better. It's to say that we can tighten this whole thing up if we really want to. Do we need... Okay, so what we could do here, instead of making the sorted list, we could do this, right? And do that again here. Okay. You know, if we really want to take this to its extreme, we can. And we can see just how absolutely unreadable this is going to be by the end of it. For example, I'm going to go ahead and do this. And so we've... Oop. There we go. And I could take even this statement, right? There's a good chance I've introduced an error in here somewhere, and that this won't work. But you know, this is more just for fun, showing you how we can continually condense this and become really obnoxious people really fast. In fact, why don't I just do this, you know, and we'll do this as well. We're getting really far down there. And we can do, oh, one thing I forgot to do that I should have done is, okay, so this should work, right? Looks like it should work. I think, should just be able to take this even further, right? If I really want to be a terrible person. And do that. Okay. I think that should still work. Let's find out. Oh no! Okay. Well, that's really going to be hard to track down. Okay. So what's happening here? List index out of range. List sorted upper mid. List sorted. Huh. List sorted upper mid. 140. I must be passing in an index that is not great. Median of the sorted list of. See, this is the thing. When you condense something down this far, it is actually hard to figure out where your errors are. And that said, I'm going to paste this into the Slack. And if you're feeling industrious, I'm not going to track this down, at least not right now. Find my error. You know, figure out what's going on here, and try to fix it, and paste it back into the Slack. And I would take the time right now, but we need to move forward. At any rate, you can condense your functions pretty far, but should you condense your functions? That ends up being a little bit more philosophical. But, at any rate, we're going to have a 5-number summary that we can utilize. Now, why the 5-number summary? Now, this is a different question. Why do we have this thing called the 5-number summary? We have this so that we can take a quick look at things. We have it so that we can, peek into our data and say, well, what's the minimum? What's the max? What's the median? Where does that Q1 sit? Where does that Q3 sit? And we can get sort of like an immediate view of the shape of our data. And, what do I mean by shape here? It's just, where are these moments in the data? Where do those things sit? And you'll find that 5-number summary it's used. It's used in a number of spaces. I almost never use it, to be quite honest, in the things that I work on. I might use median-based metrics, or I might use mean-based metrics, L1 and L2 metrics, which I won't get into here, but I might use those, and I might use those as determiners of, variance and spread, however we want to think about this, and kind of the shape of the data. Or I might look at the distribution itself, where do these points lie? And it's really domain relative, right? The metrics, the analyses that you end up doing. 5-number summary is pretty classic. If you've ever taken, a fundamental stats course, they're going to teach 5-number summary. They're going to teach a lot of things through it, and you're going to build box plots out of it and everything. If you are in digital image processing, you're probably not going to ever touch a 5-number summary, right? So it is really about the domain. Okay, so I'm going to just demonstrate a quick example, another quick example, and I've got these two lists of numbers, right? And I don't think there are repeats in any of these. It doesn't look like it. Okay, so if we calculate the 5-number summary for these, let's just look at 5-number summary of A. I'll just print A, and the 5-number summary of A. We'll do the same thing for B. Okay. Let's also look at the mean. Okay. And I'll just do it like this. I'll print the mean of A and print the mean of B. And then I'm going to ask a type of foolish question that that I might be prone to ask. Looking at A and looking at B, which do we think mean or median is the better measure of centrality of the data? And I'll make this a little bit bigger so we can kind of like think about this. And okay, so I'm asking which is the better measure of centrality? The mean, which we're seeing for A as 11, and we can see it here, the median is 9. Or for B, the mean is 25 and the median is 19. Right? Like, how do we want to think about this in terms of one measurement being better than the other? And what I'm going to say, and you are very welcome to disagree with this, is that neither of them is better. Exactly. They're different lenses on the same data. But what we can say is that 11 is sitting pretty close to 9 in this one, right? Like 11 is just right of 9 in a way that looks like there's some alignment of the median and the mean. And in this other case, 25 is a little bit more estranged from our median of 19. But does that matter? Like, I think looking at both of these actually gives us a sense of the shape of the distribution, right? We've got, over here, we've got our Q3 pretty far to the right, you know? And I think, you know, when we're looking at this, we want to think about this in terms of the shape and not which is better than the other. So that's just some food for thought. And after today's class, we probably won't touch on median very much. It'll come up a couple times, but not so much. Okay, so next, we've got this function, this 5-number summary function. And, you know, what are we going to do with it? We're going to take an approach for determining outliers. That's how we're going to think about this. There's this thing called the IQR. And the IQR, this might be easier to show, actually. Well, okay. IQR is very simple to explain. Right, we've got our min, we've got our max, we've got our median, we've got Q1, we've got Q3. The IQR is the values included in the range of the IQR are those values between Q1 and Q3. Right? That's kind of the middle 50% of our data. All right? The way we determine IQR, and this is a single numeric value, right? This is just a single scalar value. It's a measurement. Our IQR is simply Q3 minus Q1. Okay? That is sort of the range that the middle 50% of values falls into. So it has kind of the min of the IQR and the max of the IQR. That is going to be our most, we're going to think about that as a representative portion of our data, right? It's sort of like taking the median and expanding it out to be, you know, like inclusive. We can kind of think about this as, you know, when we're looking at something like, you know, some kind of distribution. We can think about something that's a little bit normal-ish. We're often interested in the most commonly occurring stuff. And although IQR doesn't really tell us the most commonly occurring stuff, it does give us some idea of some middle and something that's representative. Now this is, you know, a little bit misleading because it's a normal distribution, but we could think about this as like if we have a bunch of equally probable numbers between, I don't know, say 0 and 50, there is going to be this middle 50%, right? 50% of our values are coming from here. And we can think about this as the IQR, and we can kind of think about it as being representative of our data. Okay, so it's going to be really easy to code the IQR given the 5-number summary. And what I'm going to have you do is exactly that. I'm going to have you code the IQR, give you 4 minutes to do so, and I'm going to give you some dummy data to work with. So you're going to have list A and list B. Oh, and mean is good for A, while median is better for B, since it seems there's some outliers that might be skewing the data. And I think that's very appropriate, especially if we're thinking about a business case. And I also want to, you know, reinforce this idea that it's not that one's better than the other. It's that they, you know, their relationship gives an idea of the shape of the data itself. But in the business problem that you end up solving, often you're going to pick one over the other, and that's very appropriate depending on what you're trying to solve. Okay, so go ahead and get started on that. I'm going to set a timer for 4 minutes. Your IQR function is going to utilize the 5-number summary function, and remember, IQR is simply Q3 minus Q1. Okay. So let's go through this. There's our numbers. I'm going to go ahead and write the function above this. So the function IQR here is very simple. We can just say IQR of a list. We're going to get 5-number summary of that list, and there are going to be 5 things that get out of this. We're going to get. Notice I'm using an underscore here because we don't care about the min. We're just going to throw that away, and so we get the min. We get Q1. We don't care about the median. We do care about Q3, and we don't care about the max. So we do that, and we can just say return, and this is just going to be Q3 minus Q1. So that's our IQR function. And next we can, we want to print what do we want to do here? Let me just double check. We wanted to print, we just want to print the 5-number summary and the IQR of each. Okay, so I'm also going to print I think this is good practice in general, the sorted version of A, although, it's the same as A, right, given the way that we built that. Then I'm going to print the 5-number summary of A, and I'm going to print the IQR of A. And I'll put just an empty space there and change those to B. And let's see what we got. Okay. So here, in this case, in the case of A, we have an IQR of 25. That gives an indication of the spread of the middle 50% of the data. And in the next one, we have an IQR of 50, which again gives an indication of that spread. Now, where is that coming from? I think that makes sense. This is pretty intuitive. It's just 0 to 50, right? And then 0 to 100. And so that middle 50% is expanding from 25 up to 50. I think that's a pretty intuitive thing to see. Okay. All right. So I think here's what we're getting at. Teaching this is a little bit like, okay, well, let's build a procedural understanding of this. Easy enough. We can grab the IQR. How might we use the IQR? It turns out that there is a classic way of determining outliers. Okay, and that is, we take the IQR. Okay, so we take the IQR and we multiply it by 1.5. So whatever this is, whatever this ends up being, let's call this, let's call this X, right? We can take Q1, right? We can take Q1 and subtract X from that. So we can take whatever this is, subtract it from Q1 and decide anything below that is a low outlier. And anything that is X above Q3 is an outlier, okay? So let's kind of back that up. There's this arbitrary number we've decided. It's not completely arbitrary, but let's just say that it is 1.5. So 1.5 times the IQR. Sorry for switching my operators, but 1.5 times the IQR. This 1.5 is this is arbitrary, right? I'm going to call this an outlier coefficient. So I'll call this outlier coefficient. And what we're really saying is the outlier coefficient multiplied by the IQR is going to give us a value that we don't want to exceed above Q3, or below Q1. And in practice, in modern practice, we want to be able to change this coefficient, right? We want this to be adjustable. 1.5 is classic, but if you want to have like a systematic way to approach determining outliers, a simple systematic way, you probably want to be able to adjust your coefficient. So anything that is Q1 that is below Q1 minus the outlier coefficient, so I'll call this just out coefficient, times the IQR, and anything that is greater than Q3 plus that coefficient times the IQR is going to be an outlier. We're going to describe it as an outlier. But again, this is arbitrary. You want to be careful about how you think about this or how you apply this sort of thing. Okay. So I'm going to have you write a function here. Let me just get this up here. You're going to write the detect outliers function. And you're going to return all your outliers in a list. Notice this is returning a list of outliers, okay? So keep that in mind when you're writing it. An outlier is, as we described, it's that outlier coefficient, which I'm giving you the header for this. It's that outlier coefficient multiplied by the IQR above, or above Q3, or below Q1. Anything that is outside of that. Okay, and I'll also paste this in. Just go ahead and get started. I'll start a timer in just a second. right, so I'm going to take us through a solution. Let me know if this particular function is sort of more challenging, or if it's not clear how to go forward with solving it. I'm going to talk through it. Maybe I'll try to talk through it a little more extensively, but so this is called detect outliers, right? Detect outliers, and maybe I'll make that a little bigger. And we're passing in the list, and we are setting an outlier coefficient. By default, that coefficient is going to be 1.5, which is the classic coefficient for this. So if we are trying to determine 1.5 times the IQR above Q3, then we need some things, right? We need Q3, right? So we can do that. We can just grab, we can reproduce this little bit of code up here, right? And we can go from there. All right, so outliers, it's going to be an empty list. And we can check every number in our list, okay? We can just walk through that list and determine if it's less than or greater than Q1 minus the outlier coefficient times the IQR, or greater than Q3 plus the outlier coefficient times the IQR. So we could do something like, why not? We could say outlier coefficient multiplied by the IQR, and then we can reuse that. And so that'll be, I'll just call it res, and maybe I'll put this above that. Okay. And then we can say for each number in our list, we can just ask this question. If the number is less than Q1 minus that result, or if the number is greater than Q3 plus the result, if one of those is true, it's an outlier, right? Or we're going to consider it an outlier. So I'll say outliers.append, and we'll append the number. Then we can just return outliers. So what are we working with in terms of, let's see, did I give us any test data? No, but I'll just make something up really quick. So let's test our outliers, and we'll do the range from 0 to 100. And I'll just make this a list. And now let's put something in here that we're pretty sure is going to be an outlier, right? So test outliers.append. Let's append, I don't know, 1 million. Pretty sure that's an outlier. Let's find out. So detect outliers, and we'll pass in this test outliers, and we're going to use this coefficient, the default coefficient, as it is. So we should collect this 1 million if there wasn't an error. Okay, float and function on line 159. What am I doing there? Oh, that makes sense. Sorry, Q3 minus actually IQR of the list is what I should do. Okay, so we're collecting 1 million. What if we appended also a different number? Let's append 300 and find out, is 300 an outlier? Turns out it is, right? And I don't think that should be too surprising. I think if we saw a list of numbers 0 to 100 and then 300, that would look a little anomalous, right? What about 130? 130 sits in there pretty well, even though we might think of that as being anomalous. Actually, we might be like, oh, 130 seems strange if you have this sequential series. So in a way, we can only detect anomalies within certain bounds, right? Like we have this pattern where we increase by 1 every time. We can't sort of figure out systematically using this method if we've skipped up 30, whether or not that makes sense. I think we would think of that as anomalous if we were paying attention to it, but systematically this is not a tool for determining that. So put that in there. And there's one more function related to outliers where we can think about this. Let me find it. And I'm actually not going to do this as a breakout. I'm just going to show you. So what if we wanted to remove outliers, right? So what if we wanted to remove outliers instead of just detecting them? How would we do that? So we pass in a list, and then all we really need to do is we need to detect our outliers, okay? So we're still going to need an outlier coefficient if we're going to build this from the prior function, right? And by default, we can just continue. We can have that as 1.5. Okay, so if we're thinking outliers, we can go ahead and detect those. I'm just going to do this and change that to detect. So then we're going to have a list of outliers that we can then remove, okay? So I can say for each number in our list, in that list that we originally got, and I'm going to collect everything into a new list. I'll start that off as empty. For each number in our list, if the number does not exist, is not in our outliers, then we can append it, right? So this is one approach. We can say output.append the number. And we can return the output. So this is kind of an additive approach. We create an empty object, and then we go ahead and fill it in. So I have a list of numbers down here that maybe I'll just test this with. We didn't do this problem, but this data is related to housing sales in in Sacramento? I can't remember offhand, but that's okay. So there should be a couple outliers that get removed here, and it looks like they did. So what was that? 350, I believe 408 was removed, and then this 1.285 with that outlier coefficient. Okay, so this is an additive approach, as I said. I want to also show you how to think about this in a more reductive way. So we get these outliers. Obviously, the list of outliers is going to be smaller than the original input list. So it might be nicer to iterate over our outliers. So for num in outliers, and then instead of, we would then want to check to see, we would then want to remove each of those numbers from our output, okay? But at this point, output is empty, so we want to actually fill output in and then reduce it out. So if you get what's happening here, we make a copy of our input list, and then we check only what's in outliers and remove those specific things. So this is a different algorithm for the same result, and we should see exactly the same. If you think about it, this reductive approach is a little bit more efficient. It'll have to be a little more efficient. Okay. So let's, since I think that's it for the outliers. It is. So let's take a break. Let's take a 6-minute break. When we come back, we'll get into variance, standard deviation, and we'll probably be able to move on to the next materials, the next stats class materials. At least we'll be able to touch on them. Okay, I'll see y'all back here in 6 minutes. Okay. So let's get back into this. If you can imagine the measure of spread that we were just looking at, the 5-number summary, is heavily related to median. We're not really thinking about the mean in that case. And we're going to switch over to variance. Okay, so this idea of variance. Variance is directly related to the mean. In fact, it is the average squared distance between each data point and the mean. So this is the average squared distance between each data point and the mean. And remember, we have a couple different symbols for the mean. And this is going to come back into play for variance. We're going to want to think about this. So we have the idea of a population, right? And we'll revisit this a little bit. We've got a population. We've got a sample. The idea of a sample. A population we can think of as being everything, right? So it's everything. And a sample is going to be a selection from the population. And, so we want to make some representative sample, we're sampling from all over this thing. And then we're making measurements based on that. The symbol for population mean, right, is mu. It looks like that. It's like a U with a tail in the front. And for a sample, the mean is x bar. So following the same convention, we're going to have, for the variance, we're going to have a Greek symbol. And for the sample, we're going to have a Latin symbol. So this is sigma. And the variance is represented by sigma squared. Okay, sigma squared. The variance of a sample is going to be represented by s squared. Okay. So we have variance, and so we have a squared in here, right? We've got this squared in here. This is going to come back around in just a moment, but we want to think about variance and a related measurement called standard deviation. Whereas variance is sigma squared, standard deviation is sigma. Whereas variance is s squared, standard deviation is s. Okay? How do you get from s squared to s? Well, that's easy. That's just the square root of s squared, right? How do you get from sigma squared to sigma? That is just the square root of sigma squared. So it'll be really easy to get the standard deviation if we know the variance. So there are two formulas for variance. And the reason there are two formulas is that we have populations and we have samples. And we want to distinguish between the variance as we represent it for a population, and the variance as we represent it for a sample. So let me show you population variance first. And what you're going to see is that the two equations here are almost exactly the same. There is a slight difference between them. So, oops, don't know why I just zoomed in. There we go. All right. So for the population variance, we're going to have sigma squared is going to be the sum of the squared distances between each data point and the mean divided by the number of data points. Okay? So that is just the average. If we're dividing by the number of data points, if we have n data points, then we're going to just multiply the sum of these squared differences by 1 over n. So we're going to use this symbol, the summation symbol, and we're going to start at the first item in our list of numbers, and we're going to go to the last item, which is the nth item. Okay, so this is just a symbol for indexing, right? In math, we'll usually start indexing at 1. That's how we normally represent that. So our index is 1, and we're going up to the last index, which is n. And this is just the differences, okay? So the difference between each data point and the mean. So the data point we can represent as x sub I. Now, why do we represent it that way? We can imagine that there is a set of data called x, and x is going to have, I don't know, 1, 3, 5, 7, and 9 in it. And we're going to say x sub 1 is going to be this first item. I want you to notice that's different from Python, right? That's x sub 1. That's different from Python. In Python, we would call this x sub 0. So just be aware the difference between our mathematical notation and how we might index something in a programming language, or at least in Python. So this is each data point and the mean, right? The mean being mu. And then we're squaring that. Why do we square it? Does anybody have a quick, easy explanation for why we might be squaring these differences? Any thoughts on that? Yeah. The simplest explanation is it accounts for negatives. We're not going to worry about negatives in this approach, and a good response to that is like, well, couldn't we just take the absolute value? And yeah, there's a different metric that we could use where the difference here would be that we don't square it. We would actually take the absolute value. The mean absolute deviation is that metric. But if we were to run through this, x. So what is the mean here? It's going to be 5. So if mu is 5, in this case mu is going to be the same as the median, but mu is 5. We could say each data point, so we would say 1 minus 5 squared plus 3 minus 5 squared plus 5 minus 5 squared, 7 minus 5 squared, 9 minus 5 squared. And all of this is going to be divided by 5. And that should give us our variance. If we wanted our standard deviation, we would just do this. We would just take the square root of whatever that value is. So this is for a population. This is our population variance. And I want you to consider something here. If you know everything and you're measuring everything, when you get the variance, that is the variance, right? That isn't a guess at the variance. That isn't an estimation of the variance. That is the variance, right? If you're sampling, every time you sample, you're going to get a different variance, unless you happen to get the exact same sample. You're sampling from a population, but you're going to have different elements from that population included in the sample. And as a result, think about this. As a result, your mean is going to change, right? Your x bar is going to change. It's going to be different every time. So in this case, if we're looking at building the variance every time, so x bar could be, it's from this sample. X bar is going to move around. The variance is going to change. And to account for including the mean in our span of variance, we actually end up adjusting this equation a little bit. Okay, So we have a slightly different sample variance. Where we apply something called Bessel's correction. And this is one of those funny things where the more you look into it, the weirder it is, actually. But I'll just hint at that. I'm not going to go into much detail. So remember, s squared, that's how we represent the variance. We use a Latin-based character for a sample. S squared is going to be, we're still going to do that summation, right? So we start at 1, go up to n. For every data point, x sub I, minus, instead of mu here, we're going to say minus x bar squared. But this time, instead of multiplying by 1 over n, we multiply by 1 over n minus 1. Think about the effect of this. Think about the effect of this. Just this part right here. 1 over n minus 1. 1 over n minus 1 is going to be a smaller, it's going to be a smaller number, sorry, a larger number, excuse me. It's going to be a larger number than 1 over n, right? So if this is a larger number, we effectively grow the bounds of our variance. We push it out. We say that the spread's a little bit larger. And when we do that, we're more likely to include the actual variance. And we're much, and obviously we're more likely to include the actual mean. But we're more likely to include within that bounds the actual variance. And in that way, we are adjusting the bias of the sample. Like, our sample is going to be opinionated in some way. It's going to be biased in some way. And it has a chance of getting it wrong. If we make this little adjustment, we grow the variance so that we're just more likely to include the actual population variance. I think I mentioned this thing before where ideally we always want to move, say, x bar. We always want to try to get x bar in, as close to mu as possible. And, we can similarly say, incorrectly, but similarly say, we're trying to get s squared as close to sigma squared as possible. That's not actually why we're doing this. We're doing this because we want to try to include, or we're trying to include the variance, the actual variance. So this is not our goal here, even though it seems like it should be. The issue with this is actually is that this x bar is always changing. So we're just moving x bar all over the place, right? And x bar is changing. Our samples, the actual sample items, are changing. And so, even if we do this over and over and over again, we're not necessarily, pushing our s squared toward our sigma squared. So be careful if you're describing that. Okay. So now that we have this basis for understanding variance, I'm going to have you code the variance function. And let's see, I need to try to fit all of this on one screen. There we go. Okay. That says that determines up here. So you're going to code the variance function. Make sure to include a parameter that determines whether the data is a sample or population, and apply Bessel's correction accordingly. Okay? So if you imagine what that is, it could just be what I would say, what I think is best here is just to say, include a parameter that is sample is true by default. Because we're almost always working with samples, and let's default that to being a sample. So that's what I'm going to have you code up. And let's see, I'm going to give you 5 minutes to do that. So go ahead and work on that. I might extend it an extra 2 minutes. When we get down to the 1 minute mark, I'll see where people are at, and we might extend it a little bit. So yeah, go for it. If you have questions, put them in the Slack, and I'll do my best to answer them in the Slack. Okay, let's see. See a few solutions in there. Looks good. Okay, yeah, we're just gonna go through a solution. And if you're still working on it and want to continue working on it, this is gonna take me a couple minutes anyway, and I will paste it in after we get to a good spot. Okay, so this is the variance function. I'll make this a little bit bigger, sorry. And I'll just pull this down as well. And just like with all the other functions, we are passing in a list, and we want to do a different thing if it's a sample, right? If it's if it's sample versus population, or population versus sample, we want to do something different. So we're going to pass in a list, and I am going to set sample to true by default, since we are usually thinking about samples. We need the mean, right? Everything we do is compared here to the mean. So we can get that, the mean of the list. And this is an accumulator pattern. So I'm just going to make a simple accumulator called total. And maybe I'll just do that. And then I can look at each item in the list. For each item in that numeric list, I'm going to start summing the squared differences between each item and the mean. So the total is going to get increased by item minus mean squared, right? Now we now want to use this sample, right? So we are either going to multiply by 1 over n or 1 over n minus 1, okay? Or, we're either going to divide by n or divide by n minus 1. Something that I showed earlier is that 1 and true can both be used arithmetically in the same way in Python. So instead of asking if sample do this, else do this other thing, we can just do total is going to be, the length of that list, which is n, minus sample. So that's a simple way to handle that without needing to perform a conditional check. So let's print the variance of, let's do the range from 0 to 100, going by 7s, why not? And let's do that again, going by 2s. And see what those look like. Oh, range object has no attribute copy. That makes sense. I need to just cast that to a list, or go make that other thing type safe. But this seems like the easy way to do it. Okay. So we have these two numbers. 980 for the variance from 0 to 100 by 7s, and 850 for the variance between 0 to 100 by 2s. What is this number, right? 980. How does that relate to all these values, all these numbers that are less than 100? I think this is where people kind of check out with variance a little bit. It's hard. It's a little bit difficult to interpret. But what is easy to interpret is the standard deviation. So let's think about why variance might be hard to interpret upon first look. I'm going to do this from the point of view of, of a room. So we have some room, and let's say it's 10 feet by 15 feet. What is the square footage of this room? Right? That's 150 square feet. Whereas each of these measurements is 10 feet, 15 feet. So, oops, don't know what's going on there. So looking at this, if I were to tell, say, hey, there's a 150 square foot room over there, unless you've been working with this, or unless you think about it, you break it down, you're like, well, okay, that could be 10 by 15 feet. It's going to be hard to interpret that. So we're looking at squared, we're looking at a squared value. And what's easier to think about is actually just the square root of this. If we took the square root of 150, that would be easier to interpret than would 150 square feet. Likely, depends on what spaces you're in and how you use squared values. So some people are very comfortable with variance, and other people are going to opt for standard deviation. Standard deviation, it's the same formula as the variance formulas, except we throw a square root around it, and I'll just show that really fast. Right? Same formula, throw a square root around it, and we represent it with a single character, a single symbol, either sigma or s for the sample. So how do we write this function? It's pretty straightforward. We can just do def standard deviation, and we pass in a list. We say, sample could be a sample, right? And then we can return the variance list sample and take the square root of that. So raise to the 1/2. We could also say from math import square root. Either one of these is going to work. I usually do this, but it's really up to you. And then if we look at these results, they're going to be much, much easier to interpret. Right? These are in the units. These are in the units of our original lists, right? So 0 to 100, we're looking at a variance of 31 if we're traveling by 7s, and we're looking at a variance of 29 if we're traveling by 2s. In both cases, we're assuming that these are samples. Let's, just for fun, let's look at the difference between, let's do this for both variance and for standard deviation. And I'm doing this to make a tiny point, and definitely not a grand point. So let's change both of these. In fact, why don't we do this? Why don't we I'm going to do that, and let's print. Let's actually just print this list as well. And we'll do the population first. So let's set sample to false here. And we'll do that again for this. So there's a lot of redundancy happening here because I'm thinking it out a little bit as I go, but I think this should all make sense. So we're going to see, oops, I actually want to do that up here. So we're going to see the sample variance and the population variance and the sample variance for both of these. And I'm going to just take all of this and do the same thing for the standard deviation. All right. So let's see what this looks like. All right, so traveling between 0 and 100 by 7s, the sample variance is, the population variance is 914. Notice that it's constrained somewhat. The sample variance is 980. So it's expanded a little bit. And I think we're going to see the same thing for the for 0 to 100 by 2s, the variance for 0 to 100 by 2s. 833 for the population, 850 for the sample. Now, standard deviation, I just want to point this out. The standard deviation, the difference between the standard deviations for population and sample are much, much more subtle, right? This is a little more than one difference, right? Like we're looking at something that is maybe not significant in the sense of, how we think about significance in statistics. So do we need to use Bessel's correction for standard deviation? That's a philosophical question. There's a lot written on that, actually, and there are different camps that believe we should or we shouldn't. And the reason I'm pointing that out isn't to, hopefully isn't to be confusing. The reason I'm pointing it out is just to express something that I think we see in statistics quite a bit. We have to be critical, right? We have to use our critical thought, and clear conclusions are still sort of out on a lot of things. I think in math in general, it's a little different, right? You get these systems, these closed systems that work well, right? You get a clear sense that, this is how the quadratic formula works. It's not really contested. Nobody's really arguing around it much, if at all. And every once in a while, something will blow open this hole in the side of math just a little bit, and then it seals up really quickly. And barring incompleteness, if you're into incompleteness at all, math tends to be a system that works really well within itself. Statistics is a little strange, though, because we're always having arguments about whether or not something works or is appropriate. And part of the reason is that statistics is it's math. Yeah, it's mathematical concepts, but we're really considering things in the real world which don't always obey in the way that we want them to. And so, here's Bessel's correction, for instance. Bessel's correction makes a clear difference when we're talking about variance and when we're thinking about variance and applying variance. But when we just take the square root of the variance, it doesn't matter as much, right? And quantifying it mattering is something we can do, and some people are going to say, okay, well, according to my threshold here, that doesn't matter. And according to your threshold, maybe it does. I think it's important to, with that in mind, to try not to say very concrete things when you're not sure that they're concrete, right? Sort of like going back to that idea of, well, there are going to be times where median is much more appropriate to use than mean. That's going to come up. And the way that you're going to qualify that is looking out into the real world and saying, hey, does this phenomenon work the way that I think it does? Is this thing that we've measured an outlier? Is it clearly an outlier? Or maybe there was some misrepresentation in our data. Maybe we recorded this incorrectly. That kind of thing does happen. That happened last year with the Data Europa COVID data, right? Where there were a couple of things that I noticed that were anomalous. It was just like the recording for a day, like, in a country where there was 20, 30 cases per day, and then there's this day that has 1,020 cases, right? Like, you see that and you're like, oh, that's an anomaly, right? That looks anomalous. But what if it wasn't, right? What if there is an extreme case, an extreme instance of samples where that is actually representative of the phenomenon? Then throwing that piece of data away may not be appropriate, right? So when we're thinking about, again, back to median and mean, there are business cases where you're going to choose one over the other, for sure. But what I want to sort of just reiterate is it's best to not think of one as being better than the other, but thinking of both of them as being measurements on the same phenomenon. Okay, so let's get away from the abstract a little bit. And I'm going to get us started on the next set of materials that we're going to look at for stats. So that's all we're covering for summary stats. There are other summary stats, just to be clear, that exist out there in the world, and there are other things that are going to come up, like things like distance metrics. Okay, Euclidean distance versus taxicab distance versus sort of different norms that you construct for different dimensions of distance. There's things like cosine similarity. There are all these different metrics on our data. Okay, often we'll be comparing two sets of data or something like that. These are the core, and we cover them primarily because we can express them with Python very easily right here, and they're already fairly accessible. I think most people in here have heard of all of these at some point or another. Okay. So this is going to feel a little bit like a hard turn, but we're just going to start. We're going to start in on this, and we're going to see where we get. Okay. So there's this. There are some bases for understanding. Well, let's say there are some bases for understanding probability, and understanding probability and statistics, for that matter. And one of the ways that we're going to approach understanding probability is through ideas in set theory. Okay. Another way that we're going to do this is through sampling, counting, and these are often more like hands-on, intuitive, procedural, right? We can write some Python that is going to sample. We can write some Python that's going to count. But we're going to actually relate these back. We're going to use set theory as a starting point. And then we're going to relate these sampling and counting back to set theory. And I think that's a nice way to do it, because I don't want you to think that sampling and counting are separate things. I think we could start anywhere. We could start with set theory as an abstract, and then work with sampling and counting, which is what we're going to do. Or we could start sampling, right? Or we could start counting. Any of those things are inroads. But I think starting with set theory, in a way, builds a nice foundation. So, what is set theory? Well, let's think about this first. Let's think about what is a set. And oh, sorry, I just noticed that somebody asked a question. Let me just jump back over there. Oh, I would like to answer that question. That is a great question. Where would you use Euclidean distances and cosine metrics? Yeah. So how should I answer this? Let's say you have an image. So you have an image of, I don't know, let's say there's some mountains and, sunset. And you have another image taken, this is actually, let's say, a copy of that image, and you've reduced the resolution somewhat, right? So, fundamentally it's kind of the same thing, but this is, you've reduced the resolution and then increased it, so it's still the same size, we could say. We can look at the distance between these two images. And in that sense, the distance is kind of the difference. And we could take a Euclidean distance between them. We could think about this. We could take this image and we could unwrap it into a single long vector. So this is, image 1 and image 2. And we could unwrap this into a single long vector where, instead of two-dimensional, we're taking each row of pixels, if you imagine each of these as rows of pixels, and we're just placing them end to end, we could compare these, we could use Euclidean distance to compare these, right? Where the length is the number of dimensions. So that's something we could do. And it may not be the best thing for us to do. We could also use something called mean squared error. We could use cosine similarity. And all of these are going to give us different representations of the similarity or differences between these two objects. And that's not the only way to determine or quantify the similarities or differences between these two objects, but Euclidean distance is one of the ways that we might do that, where we often will go to Euclidean distance. However, Euclidean distance doesn't work well in high dimensions, so we tend to figure something else out. That said, distance metrics become fundamentally important, and we're constantly figuring out how far away we are. Let's say we make a prediction of something. How far away is that prediction from reality? And you can think about that as being a distance, right? So you guess that the stock market is going to go up. Some stock is going to go up like some number of points, and you get it wrong by a certain amount. The amount that you got it wrong by is a distance, right? So I think about this a lot in terms of images because I do a lot with images. And we're constantly quantifying different forms of similarity between them. One of the things we can do is Euclidean distance or mean squared error or something like that, but we're probably going to use a different distance metric for images specifically. But Euclidean distance will come up a lot, as will taxi cab distance, as will Minkowski, which is sort of like the abstract of the two. Anyway, there's a lot of them, and they will come around. So let's just define a set. Let me get back to the color black here. So what is a set? I'm going to describe a set as being a few things. I'm going to describe it as being unordered. Doesn't matter what the order of elements in a set is. I'm going to say a set is composed of elements, okay? Composed of elements. Keep in mind, an element can be anything, right? An element can be another set, okay? So an element is just a thing in a set. The way that I'll represent this is, let's say I have a set and it contains these elements: 1, 3, cat, and 9.2. So I have this set. There is a subset of this, and I'm going to call this set A, by the way. Let's say there's a set B, and it contains 3 and cat. B is a subset of A. So all the elements that are in B exist in A. A very important, or a part of an aspect of sets that's going to be very important for us is that we cannot have duplicates. So composed of elements, these are unique elements. So this is very important. There are no duplicates. There are a number of things that we'll think about with sets, but I'm going to give you sort of a glimpse into the probabilistic idea, which is going to come around later. If we have a set, and I'll call this set C, and it has the items, the elements 1, 3, 9, whatever number that is, I don't know what that is, 7, 12, and 13. These don't have to be in this order. right? They could be in any order. And we have a subset of C, which is going to be D, or we could call it C sub or something like that, but call it D. And this has elements 1, 3, and 9. What is the probability of selecting subset D, some aspect, some event, some element in subset D from the containing set C? Turns out it's the size of D, which is 3, or the magnitude, or what we call the cardinality. That's going to be 3 over 1, 2, 3, 4, 5, 6. Notice we're making some assumptions here. Every one of these events is equally likely. Okay, 1, 3, 9, 7, 12, 13. We need to state that explicitly. And for D, 1, 3, or 9 is equally likely. And so if we're considering the probability of D, this is going to be what we call the cardinality, or the size of D over the size or cardinality of C. And that's something that we can compute. And that is a pretty good basis for understanding probability, right? It's, you have all these possibilities, and there is some strict subset of those possibilities. And we're asking, well, what is the probability of getting something that is in that strict subset? So there are, we're going to think about sets sort of in regards to a concept called an experiment, which is a word I think all of us know very well. I'm going to call this a random experiment, okay? So a random experiment is, a thing that we do where we don't know what the outcome is going to be, simply enough. We flip a coin, we roll a die. And let's use that flipping a coin concept. What is the set of outcomes for flipping a fair coin? It's going to be heads or tails, right? That's what that is. What's the outcome for flipping a four-sided die? It's going to be 1, 2, 3, 4. What is the probability of getting an odd number when you roll a four-sided die? Well, it's going to be 0.5. What's the probability of getting, we can see that. It's just these two items divided by the total number of items. What is the probability of getting a number less than 4 when rolling a four-sided die? Well, there's 3 of those. So that would be 3 out of 4. So this becomes a fairly convenient way of thinking about probability, especially at the beginning. And there are a number of operations in sets, a number of operations, and I'm going to focus on this a little bit. Set operations are going to be equivalent for us to logical operations. Okay? We've been using logical operations, right? We've been using and, or, not. Sorry. I kind of put those in something like the wrong spot. I don't know why it's not erasing. I should really put those under logical. So, we've got these, we've got and, or, and not. These, we use them all the time. The equivalent set operations are intersection, or let's say intersect, union, and complement. I don't want to say these are the same thing exactly, but they're analogous enough that we can use them to construct, we can use them in almost the exact same way. And we can actually rethink how we think about logic, or we can rethink logic to be about sets, and vice versa. So we'll get into that in the next stats class. We'll review random experiments really quick, and we'll go a little bit deeper into how we think about sets. And then we'll just write a bunch of code that performs our basic logical operations from a set standpoint. And yeah. So that's lecture for today. Have a wonderful evening. Feel free to sign off. I'll stay on for questions for a few minutes. And yeah, what I would say is if you struggled with the functions today, review them. Go back through and review them. These are sort of, kind of foundational. And we're going to be doing more complex things later on. So, yeah. At any rate, have a wonderful evening. And I will see you all. I believe I'm teaching Thursday. Clark will be teaching tomorrow.